Hello students, welcome back. We went through the concept and theory of continuous random variables. Now let's establish the concept of expected value, variance, and standard deviation. We are using probability density function instead of probability mass function. And we are using continuous sum instead of discrete sum. Continuous sum is an integral. So here we go. Instead of adding everything, we are integrating everything. So x value, payoff value times probability mass as before, but not probability mass, probability density. That's a bit of a difference. Otherwise, same as before. And if you have composite random variable, then as before, you just have h of x as your payoff, and that's it. See the association there? Expected value of x used to be for discrete random variables for all I values starting 1 through whatever. And this was the expected value computation. Payoff times the probability mass, and we have finite sum, or sometimes we have discretely infinite sum. But here we have to have continuous sum. We have an integral. So instead of sum, we have integral. And then instead of probability mass, we have f of x dx, density times dx. And the same thing is going on for these. Variance and standard deviation, again the same deal. X minus mu squared, but this part, f of x dx, stay the same. Standard deviation is nothing more than taking the square root of the variance, so it's not really that of an issue. Let's see, shall we do some application problem, how to calculate those? Okay, here's an example problem. All right. F of x is given like this, and determine the coefficient of a. All right. Total probability is always 1, so integral of the density function is always 1, from negative infinity to positive infinity. And a is constant to take it out, so what do you get? A is 1 of that integral. Calculating that integral, in this particular case, we needed integration by parts, so I'm not going to go too deeply into it. If this integral had been some simple integral, then my expectation is that you do this integral. But if this is a bit of a complicated integral, then you can use Mathematica over from alpha to calculate it. For example, if you just copy and paste this expression here to Mathematica here, and then let it calculate, it'll calculate. That's enough for me. So the integral is 1/4, so a value is 4. In case you are interested in the integration computation here, integration by part, but that's not really part of this course. That's calculus. And assuming that you got 1/4 from here, that a value is 4, you can get that. So you got the density function now, replace 4 right here. And then you can calculate the expected value. No, before that, find the probability between 1 to 3. So integral from 1 to 3, and doing this integral, again, you ended up with a calculus problem. I don't want to go too deeply into this, unless your integral is a simple integral, something like polynomial kind of thing. If it is just integration by substitution, I'll do that, but integration by part is covered by calculus too. So I'm not going to emphasize that for this particular case. But if you encounter with easier problem instead of this, then you should be able to handle that. Now, how about the expected value computation? It's this, isn't it? So h of x is right over here, but I multiply additional x. So here is the expected value computation. It's the x times that. So we have integral of 4x squared. Oh, by the way, in case you're wondering why negative infinity to positive infinity became 0 to infinity, because when x is less than 0, we get 0. So that part you don't have to consider. 0 times something is 0, adding a bunch of 0, that's 0. So you have integral 0 from infinity only. Again, this integral computation is just calculator work because it's too complicated. You'll have to use integration by parts twice. It'll turn out this is just 1, so expected value is 1. Yeah. Now, how about the probability standard deviation? So you have to find out the variance first, and then take the square root. That's going to be standard deviation. And variance formula is over here. So in that integral, I have to do x minus mu squared times f of x here. So x minus mu squared, mu we just calculated. Mu is 1, so x minus 1 squared. And then 4x e to the negative 2x, that's the density function. So you have to calculate this integral. Well, you can break it up and apply integration by parts, but come on, you have this Mathematica software as I required. Well, here's a reason why I required. It's 1/2. So the variance is 1/2. And the standard deviation, therefore, 1 over square root of 2. Now, if you have to do this with traditional method, I guess I didn't bother doing that even here. Yeah, well, if you try to do this computation with whatever method that you use, integration by part, probably 3 times, you're not going to like it. But then again, we're using computer algebra system here. Okay. So if you want definite integral down here, indefinite integral up here, turns out this is the antiderivative function. Now, by the way, this percent notation is previous result. So this is variance. So get variance of 1/2. And square root of percent, so square root of previous expression. So that's the standard deviation. The detail is left to the students. After all, this is highly computational. Now, how much time do we have? Oh yeah, plenty of time to discuss the properties of expected value. Okay, all right. Expected value has this property which we already discussed for summations. And does it work for integrals? The answer is yes, and it's actually easier. You see, by definition, we have this x expression and then the density, f of x dx. All right, and then apply the properties of the integrals. Hey, that's easy. We have just distribution, and get a out, b out. And this one, that's the expected value, isn't it? That's mu. And this one, that's just 1. This one, this is 1. Integral of the density function, that's probability of everything, so that's just 1. Let's go to the next problem here. The property of variance. Same result as before, and the proof, well, similar, and as a matter of fact, compared with the discrete case, actually it's easier because students are more familiar with integrals. Let's see, variance. So this quantity minus corresponding quantity a mu plus b squared. So expected value of this, as you calculate it, is a mu plus b. You see, remember, this is mu. Too many expected value notation, that's too complicated, so express this as mu. So a mu plus b. And then algebraic manipulation, b minus b. Well, that part cancels out. So basically I have is ax minus a mu squared. Factor a out, then I have a times x minus mu is squared, and then I can take a out, a, and then square it outside, so we have a squared, and what's left is x minus mu squared. In the end, we have variance. So compared with the discrete case when we had to deal with summation, this is actually easier to understand. This property of the integrals. Everybody's already familiar with this. And I have written these kind of problems before as exam problems, and the result was generally good because probably students understand integrals better than summation. Finally, this variance is expected value of x squared minus expected value squared. So begin from the definition of the variance, x minus mu squared times, the density, but algebraic manipulation, we just have complete square, and then distribute this f, then we get, well, all those. And then just divide all those integrals. This one is nothing more than expected value of x squared, this composite function, and then f of x dx. And here, 2 mu, that's just constant. And then this part, x times f of x, that's just expected value, that's mu. So we have 2 mu squared as a matter of fact. And here mu squared, and then this is 1. So expected value of x squared minus 2 mu squared plus mu squared. So after simplification, just mu squared. Enough time for one more? Okay, I guess so. The standardization. Let's consider composite random variable obtained by x minus mu over sigma. Mu is the expected value, and standard deviation is sigma that goes downstairs. X minus mu over sigma, and this quantity, random variable obtained by this computation is rather special in the sense that expected value is 0 and variance is 1, so the standard deviation is square root of 1, so it's also 1. So expected value 0, standard deviation 1, and you obtain that through appropriate scaling. You see, what is z versus x? X minus mu, so it's basically adjusting the 0 point. And sigma is basically scaling. And my favorite analogy is temperature conversion. So you see, Celsius degree is Fahrenheit degree minus 32 over 1.8, the conversion factor. So it's just scaling. The hotter it is in Fahrenheit, the hotter it is Celsius, and vice versa. And it's nothing more than scaling. The same thing is going on here. Let's go to standardization. And let's prove that. And the proof is actually easy. And you can use whatever you did before, expected value of this. So you use ax minus b like this and then calculate directly. Variance, again, you can use ax minus b like this, and then a is 1 over sigma squared. So you can prove like this using the previous result. Or you can do it directly. Expected value computation. Just by definition, this expression times f of x dx. And then simple algebraic manipulation. Take the sigma out, and what happens is x minus mu. Again, properties of integral. This is expected value, so mu. And this one is mu times... Oh, I took mu out, so this should no longer be there. Sorry about that. So I took mu out, so mu out, and this is 1. So you have mu over sigma minus mu over sigma, so that's 0. This is variance computation. This minus expected value squared, but expected value is, we just calculated, is 0. So that part just drops out. And then let's algebraically manipulate a little bit. Sigma squared out, and what's left is x minus mu squared. And then this part, density, the same. So this whole thing here is variance. So sigma squared. So what do you have? We have 1. Simple. I've written these before in exam problems, and the result was actually pretty good. I can say the same for summation, actually. I never tried, but even if I did, for discrete version, probably the square was not, probably wouldn't have been very good. But for integral, no problem. Okay, so much for section 3, and we'll meet again in section 4 for a separate video.